Welcome to the second talk of this session, where Tobias Brandt will be talking about PRQL, a modern language for data transformation. You can start when ready.
Thank you, Neil. Hi, everyone. Yes, I'm going to tell you about PRQL, as in the sequel to SQL, and a little bit about myself. But rather than introduce myself, let me introduce PRQL. So here is PRQL, and if you have any familiarity with SQL or SQL or Pandas or Polars, then hopefully the following should look somewhat familiar and won't take much introduction, but I'll introduce you to it in more detail as we go through. So the outline for my talk is why should we care about yet another kind of language, and particularly this one for data. Then I'll talk about PRQL and how its structure, and to teach you about it. And then finally we'll look at some examples. All right, so why PRQL? And the story begins on January 24th in 2022 with a proposal on Hacker News for better SQL. And I noticed it at the time. I think it was the top story at the day and had sort of over 200 comments. And the proposal that Max put forward just immediately kind of resonated with me. And it echoed a lot of the things I wished were different about SQL, and I had been looking forward for a time. So I took a keen interest, but at the time it was just a proposal. So I kind of took a note and went away and came back a couple of months later. And lo and behold, there had been a lot of enthusiasm about the proposal, and an implementation had started, and the language kind of was already growing fast. And since then, it's grown in leaps and bounds with over 8,500 stars on GitHub, despite being only 1.5 years old. And I think some people are using it in production. I think that's a little bit risky. I mean, it's still a bit of an early stage, but people are. And I think once you start using it and for your kind of day-to-day work, which I do as well, then you'll struggle to go back to SQL. So without further ado, let's look a little bit into more detail. So why start with SQL? And I think SQL is the lingua franca of data. It's spoken by all the relational database management systems. A lot of the data frame libraries like Polars and Pandas also provide SQL interfaces to their data. Data lakehouse engines like Tabular, Gemio, Iceberg, and Delta, SQL. And there's a lot of tools that actually allow you to use SQL to query any kind of data. Like there's a package called OS Query with which you can query the state of your CPU and the operating system. There's a tool called MergeStat with which you can use SQL to query your Git repositories and GitHub. So SQL is really a lingua franca, and it's got two main aspects that I think are important, and it's relational and declarative. And the relational, I'll go into a little bit more detail just now, but the declarative nature is that you declare what you want as the outputs, and then the query engine has a lot of freedom to optimize the query and produce those outputs for you, which stands in contrast to imperative programming type approaches where you tell it what transformations to do. And if you look at things like Pandas, they also, because it follows that sort of imperative paradigm, it follows an eager execution model, and hence the query engine can't do the same level of optimizations that SQL can. So SQL is clearly very useful. It's been around for 50 years, and many people believe SQL will never die. So let's look at what that is. And I think at the foundation of that is that it's based on relational algebra, which was really sort of milestone in the 1970s, which was an abstraction over the data storage. And you have various operators like projections and filters and joins. And I mean, I won't go into too much detail there, but I think given that it's like a solid theoretical mathematical foundation, you can see why people believe that it will stick around for a long time, because it's really fundamental to thinking about data. And people often seem to confuse SQL with relational algebra because it's the only language that really sort of embraces relational algebra. So there's often it's sort of conflated. But I think we can look at the relational algebra and then look at SQL. And SQL itself is a bit of a sort of patchwork of things. It's grown a lot over the last 50 years. And while it started as sort of a structured query language, and it's supposed to look like English, so that you could read it, like select these fields from a particular table of records. As the needs of the data processing community have grown, the syntax got patched with various like additions, and it's kind of become inconsistent over time. And it also kind of just looks antiquated, like with the caps, it sort of looks like COBOL and not like modern languages that we work with. So I think one of the really big problems with it is that it's not really composable. So there are things like you can have these nested subqueries, and like with modern SQL, you also have common table expressions and views, but fundamentally it's quite difficult to build up a composition of primitives that allow you to build on work you've already done. So it sort of seems like every time you want to do something, you have to start writing queries from scratch. And I think that really throws away one of the main powers of programming, that we start with some primitives and we build up libraries and we build up tools based on that really, like, the famous Python slogan, batteries included. So you can pick up the tool and really be productive from the word go. Then the syntax is also not really consistent. So in the first line here, we have an alias where we say we select the name from the table albums and we give it like album name as an alias. And then depending on which SQL dialect you're using, sometimes you can, in some clauses you can use the alias, in other clauses you can't. So that makes it also quite difficult to use, because you have to remember a lot of specific rules as to when you may use an alias, or what like fields you can use in which parts of a query. And finally, as I've already mentioned, there have been a lot of dialects that have emerged over the years as people had needs and the database vendors wanted to include new functionality. So they kind of introduced their own syntax, and then if it became popular, it got adopted by other ones. But overall, it's just there's quite a lot of inconsistencies between the different dialects. And in the past, that maybe didn't matter so much, because if you were a Microsoft shop, you would use SQL Server and you just would know T-SQL and SQL Server, or use Oracle or the Postgres flavor. But these days, where we're working with data warehouses and we pull data together from many different tables. So you might have some data sitting in Snowflake and another in your Postgres OLTP database and some other data in Google BigQuery. So then it becomes quite difficult for your data engineer, data analyst, to keep track of what all the different dialects and how to talk between them. So while I think the relational algebra is a great aspect of SQL, there's a lot that can be improved. So how do we fix it? We keep the relational algebra, but we create a new language with consistent semantics and design syntax. and that can benefit from everything we've learned about programming languages over the last 50 years. But we compile to SQL as a backend, so kind of like a virtual machine, like the JVM or the LLM. And the reason for that is because, yeah, as we mentioned, like SQL is accepted in by so many tools, and also it allows us to move our computation close to the data. So while we love Python, the problem there is that often then if you have a lot of data to process, you first have to pull it down from your cloud data warehouse, transfer a lot of data, egress charges, and then process data locally. Whereas by compiling to SQL, we can push the computation to where the data sits and only pull down the processed results. So yeah, hence PRQL, pipeline relational query language. So coming back to our previous query, so the first thing you'll notice about PRQL is that it's pipelined. And PRQL has two pipeline operators. So the one is the pipe symbol, like in Unix, like the Unix pipe, and the alternative is the new line character. So then, that means that you can write each step of your pipeline on a new line, and the new line character will be treated like a pipeline. So looking at this query, we read it from top to bottom. So we start with our table tracks, and then we can select a number of columns. We can derive another quantity, which will be a new additional column that's added. Then we can filter by that new quantity. We can group by splitting the data set into different groups and then apply pipelines to each group. Then we can filter again and sort, and in the end we take 10 rows. So overall, I find this really matches the way I think about my data pipelines. And it also sort of matches what I think has emerged in multiple tools like Pandas, or in R like dplyr, because it just, that seems to be the way analysts tend to write their queries. Whereas the SQL syntax kind of was always a bit back to front, starting with the select and then going down, so you have to skip back and forth. Then the next big feature is that each of these steps in the pipeline is a function. So the highlighted words on the left-hand side are functions which process the pipeline up to that point. And so there's no sort of special order they have to be in. Whereas with SQL, they're like the different clauses of a query have to be written in a particular order. And for example, sometimes when you do a filter, if you do a filter after an aggregate, then that actually would have to be a having clause, where the filter up here might be a where clause. So PRQL takes all of that away, and you can just write your filters, and PRQL will compile down to the correct SQL as intended. The next big feature is that each of the functions or primitives are orthogonal. So they each do one kind of particular job, and they combine together then. So as a result, we don't have as many like things as SQL. We have a small set of primitives with which we can build up the whole language. So I'm actually going to just jump ahead to that. So yeah, that's on the point of orthogonal. So these are all the main transforms that are in PRQL. So we've got from for selecting a table, select, which selects columns, derive, adds columns, filter out rows, aggregate always collapses all the rows into a single row. Sometimes if that's inside a group statement, then it would be like one row per group. Sort changes the order of the rows, and I'm sure you can work out the other ones. But as a result, each of the functions that we have is orthogonal, and you can build up more complex things by combining them. So, for example, we don't have a distinct keyword, but you can do that by whatever you want to distinct is you can group and split the data set into groups, and then just take one row from that group. So that will create a distinct, like the equivalent of a distinct. So I think by really like embracing orthogonality, we've managed to keep the footprint of the language small, which makes it easy to learn and easy to use because you don't have to remember a lot of syntax. Then the next big feature is that it's when we really embrace functional programming, and we sort of take some sort of syntax like that from the ML family of functional languages, but it also you can write functions. So here, for example, we create a function take cheapest, which takes two parameters, parameter n, as well as a relation, which is another term for a table, but since they're not always materialized table, it could be also a view. We'll keep relation as the general term. And this function takes a relation, it sorts it by the unit price, and takes the first n. And in this function, you can then apply to any relation that you have. So a table like facts, for example. And I think that really gives you that composability that I spoke about earlier, which I feel is really like one of the key aspects of programming that makes programming so powerful, that we can build up complex things from simple things. And the next sort of big feature we call ergonomics, or sometimes called micro features, and that's what I alluded to earlier by saying, look, let's take all the nice things we've learned from programming languages over the last few years and just make PRQL nice to work with. So here we've just highlighted a few things. So we've got this @ symbol for date literals, so that also that sort of type safe and the compiler can see that, recognize them. You have operations between dates. We have f strings as in Python. So here that means you can build up strings by using column names within strings to build up more complicated strings. The double question mark is a coalesce, a null coalesce operator. So if you have a field that's optional that can be null, you can easily kind of fill in the null. We have numeric literals can use underscores to make them readable when you're working with large amounts like money or other kind of large quantities. And you can comment out lines and with trailing commas. So I mean, it's such a small feature, but anyone who's worked with SQL and Angular will know that, like, if you just quickly want to edit and experiment with a few things, the trailing commas can really come to bite you. And for us, it was quite a conscious design decision that by having each statement on a separate line, you can easily comment out lines, and the rest of your pipeline should always still remain operational, which really makes it easy to iterate and work with queries and get to the result that you're looking for. So I mentioned the transforms. So the other thing is PRQL is interactive. It's written in Rust, and we have an interactive playground which will compile queries on each keystroke. So that means the compiler can give you feedback kind of instantaneously as you go along, which also speeds up your execution cycle. And we have a principle of don't connect, infer. So the compiler tries to infer as much as it can about the query and what fields must be present or columns must be present in a particular table, rather than having to round trip to the database each time. It is on the roadmap to pull down schemas from the databases so that you have more type information for the compiler to work with. But at the moment, we're working on this inference model, but we are going to take care that that we don't lose that aspect. So as we pull down database schemas, that we'll store them in header files or some sort of metadata to allow speedy local development. And the final thing here is that we have good error messages. So because with our parser, we can do quite kind of nice error messages that really kind of highlights where something's gone wrong in your query. Right, so with that, where can you use PRQL today? First is on our playground. So if you go to prequel-lang.org/playground, there you've got an interactive PRQL compiler. It's written in Rust, compiled to WASM, so it will run in your browser. And we've also got some example data sets, the Chinook database, and we've got a WASM version of DuckDB running in the browser, so you can interactively play with some data there, and also I think upload your own data or your own queries. We also have a VS Code extension that you can download from the store. And finally, I mean, this wouldn't be PyCon's ZA talk without some Python. So I've prepared a Google Colab notebook, and I'm going to switch to that now for some interactive Python demo. Let's just see where we've got that. Here we go. Right, so I've pre-run everything to not anger the demo gods, but this all ran just now. So if you want to start using PRQL in Python, it's as easy as pip install PyPRQL. I've already gone ahead here and done that. So you'll see you just pull a couple of dependencies. That's because it's using dplyr under the hood. And then once we've got that, we can import PyPRQL as PRQL, and then you can get going. So the easiest command there is compile. So you can say PRQL.compile, and you can pick your any sort of simple PRQL query. And here we can see what I alluded to earlier, that instead of a new line character here, I use the pipe symbol to separate two parts of the pipeline. And so we compile that PRQL to SQL and then print that out. So I keep pushing the wrong button here. To show the output. And that compiles to a simple SQL query, select track from artists, and tells you what version of the PRQL compiler I used here. So to make something a little bit more interesting, I downloaded some Google stock data. It's got some stock returns for Google as well as the S&P 500 for a period of time in 2015, which comes from the R datasets collection. That doesn't do anything interesting, just downloads data here. And then we can, since this is Google Colab, a Jupyter environment, we can install our PyPRQL magic. And then we can start working with PRQL here. So we've got our cell magic as well as a line magic. So using this cell magic, we'll use an in-memory version of DuckDB. And let's just pull in some data from this Google CSV file. And let's look at the first 5 lines. And so you can see here that it returns a data frame. It's rendered nicely in our notebook with sort of 3 columns of interest: the date, the stock Google return, and the S&P 500 return. Now, something you might want to do, I mean, I work in finance, so if you have returns, you want to turn those into total return indices. Now, that's if you know familiar finance or compound interest, that's a little bit complicated. So you have to take 1 plus the return, and then take the product of that, and then in the end, you probably want to like take the sort of the 1 away again. And that's always something that's a little bit tricky to do in databases because there's no sort of native product function. There's only sum. So luckily we can use our high school maths knowledge of logarithms to turn a product into a sum by first taking the logarithm and then summing, then taking the exponent. So here we really see one feature of PRQL is that we can define functions, and they use a sort of lambda syntax here. So we're defining here a function ln1p, which is a function that x to this expression here. And what's on the right-hand side is an S string. So a lot of it is built up. S string stands for SQL string, and that's sort of our escape hatch that whenever something isn't implemented in PRQL, you can just specify what SQL you wanted to generate. One thing to take note of there, though, is that to any columns that you include or parameters, you must need to put in these curly braces. It will work sometimes without, but then the compiler won't. It won't be kind of obvious to the compiler. So in order to make sure the compiler does the right thing, you need to enclose variables in curly braces. So we define two functions here, lin1p and x1p, and then we define this cumulative return function, which takes a return r, do that, and then pipes this to the L1p function, then to the sum function, and then to the x1n function. So with that, we can now take our stock return data, and now we define a window. So if you look at window functions in SQL, quite an advanced feature, and I don't know, not that many people kind of are familiar with them, but I think in PRQL they're really quite nice. So we define a window which takes as rows everything, so there's no starting index, so everything from the start of the data set to the current row. And in that window, we just sort by the date ascending, and then we derive two new columns. We take the S&P 500 return, which was a existing column, and we pipe that through the cum_ret function, and similarly for the Google return. And then finally, and that's called a TRI, a total return index. And then finally, we just select three columns with date, the S&P 500 total return index, and the Google return index. So if I show you the output of that, it's done this calculation and it's returned it as a data frame. Now, the nice thing about this dpSQL and cell magic is that we can store the output into we can give the output a name. So we call it TRIS, for total return indices, and that will actually then put it in a data frame. So just to prove that to you here, we look at here, it's a Pandas data frame, and you could look at the contents of the data frame there, and you see it's the same as that we had up there. And now with our magic, we can then refer to that data frame in future PRQL queries. So instead of doing the Pandas head function, we could just do from PRQL take 5, which will give us the same result. Now you say, well, you might wonder, okay, what did it actually run underneath? Now I told you that, it just actually compiled to SQL. So if you look at the SQL query, we can use the earlier compile function that I introduced. So people.compile, and then here you can see the SQL query that it produced. And what's most amazing to me over this is that the sum in the window function, it had to use this over construct, and the compiler is smart enough to know that the sum has to wrap over this thing, and then the final x function is around that. So it knows that sum was an aggregate function, and it needed to include the window clause here, and then the other functions wrap around that. So that's kind of, I'm quite in awe of this, like how so simple it makes it to write quite complex SQL queries like this. So just to make it then a little bit more visual, let's say we can, because it's a Pandas data frame, we can plot it, and you can see now that we turned our returns into like a price curve, and in blue we've got the S&P 500, and here in orange we've got the Google price. And this was around when Google kind of announced the Alphabet holding company name change. So Google had a very large return. Okay, so let's do something a little bit more interesting. So this here, I do another window function where I look at the last 20 days, sort by the date, and now I take an average. So and that actually will produce a simple moving average. So if you plot that, we can see it now. I've taken a moving average of our Google share price, and you say, okay, well, I can do that with Pandas as well. But remember, this actually produced SQL, so this runs in your database. You don't have to pull the data down into Python. And something a little bit more complex, because I'm running out of time here, is an exponentially weighted moving average, which I don't know if you're aware that one can do that